Okay, welcome everybody. High-level synthesis is something that is here for a long time in the digital design. I think in educational process we kind of avoid this type of design, and we try to shrink the gap to include it. So I will start with some simple example. If I have a functionality where I need to add 3 numbers, this is a simple implementation in the circuit. And it's very easy in hardware description languages if these numbers are binaries or integers. But if they are fixed point and you did some additional functionality, like when you add the numbers, you want to avoid overflow, so to have saturation. This means some additional blocks after the adders. And if we want to improve the performance of this computation, we add pipeline. So we add registers to this circuit. Okay, a little more complex. If I have a loop where I just add numbers from some array, this is the simplest implementation. I need a register and an adder in a loopback. To increase performance, and if I can access all the elements of the array, meaning that I partition the array into elements and I unroll the loop, I can produce a circuit that is, in the best form, an adder tree. And to make it faster, I can add pipeline, I can access the data from elements in the circuits are consumed, what is the speed. And high-level synthesis is about transferring a functional description of the behavior of the circuit into the actual circuit representation. So we take mostly a circuit model in a language like C, C++, or System C. Actually, from these 3, the System C is an extension to the C++ with things that are usually in hardware. But we can take just normal C or C++ function, put it into some tool, and as an output, we get an RTL model in VHDL or Verilog used for the classical implementation process. And inside this big blue block are the automatized process of control data flow graph extraction, allocation, scheduling, binding, generating interfaces. This can be all automated. Well, high-level synthesis is not general software to logic translation. We cannot take some arbitrary code in C language, convert it to logic directly, because we need to follow certain rules. Only a subset of language is supported. And usually, code for software is designed and optimized to be run in the microprocessor, which is kind of different. We take a language syntax. So why should we use it? What's the benefit? If we look at the process of designing hardware, what we do is we create a model of the hardware and we optimize it. Without optimization of the hardware model, there's no reason why we should not go into software, because it's much easier, okay? And we also need to verify. And if we do it a traditional way with VHDL or Verilog, these are register transfer languages, writing the model is a time-consuming process for complex designs because we need to put a lot of details there. We take care of every bit and every clock cycle of the design. Considering optimization, problem here is that we get performance only after we synthesize the model into target technology. And this is a time-consuming process. And also, verification can be quite bulky. Okay, we can verify very simple circuits, but we have specific application domain that needs thorough verification. It's quite hard to debug. And if we go from traditional languages to more abstract, to the higher level, then the models are, let's say, they have less details, they are easier to build, and we can add some new features. Considering optimization, we can rely on the tool that performs assessment of the designed, of the synthesized circuit based on characterized library. So the input to the tool is not only the C code, it's also the characterized target library, either FPGA or ASIC. And the tool can help here very much. And of course, verification can be much faster due to less details, and also a lot of other possibilities that are offered in the C++ environment. It's not a generic solution to every problem. So we have specific areas where high-level synthesis is very useful. And to name a few, these are digital signal data processing, audio, video processing, networking and protocol processing, also machine learning, artificial intelligence, and also high-level, high-performance computing. One industrial example, 8 years ago, when NVIDIA designed their image processing superchip, they claimed that they were able to close the design gap in half the time due to using high-level synthesis when they designed a video decoder where the standard changed at that time for 4K video, and they were able to do very thorough testing, regression testing with hundreds, thousands of cases tested that they will be not able to do it in standard traditional RTL languages. So what do we have to do high-level synthesis? First, there are tools from the major EDA vendors, from Mentor Graphics, now Siemens, from Cadence, from Synopsys. They're targeting various ASIC and FPGA technologies. Then we have tools tied to the FPGA vendors like AMD Xilinx or Intel Altera. And there are many tools from universities, just in the two, a leg up from Toronto and Bamboo from Politecnico di Milano. This is that the tool set is now mature. This is the third generation of the principle of high-level synthesis. And we can really take something commercial or something free to use and design circuit with. Now, how to implement this into education process? If we look at the process of learning something new, first we need to remember, to understand, then we apply the knowledge to analyze things, to evaluate, and at the end, we will be able to create something new. Well, the first step is the most complex one, because to understand high-level models, the prerequisite is that you understand what are digital blocks, what is register, memory blocks, adder, multiplier, and you also need to know the C language syntax. This is a prerequisite to use any of high-level synthesis. And then to apply this, to create a model, okay, you need the tools. And we see that there are a lot of tools available. And working with the tools, we can write models, we can simulate, we can check the performance, and at least for electrical engineering, it's very important that we have some hardware, not only models. We on this. And this process is taught, then we are able to start with high-level synthesis. Well, the challenges here, specific to education, are, first of all, to select the right algorithms. I don't want to spend a lot of time just at what will our, okay? These are algorithms from signal processing or for some simple. These are the good candidates. The second challenge is how to properly use the language and the tools. The tools are not specifically designed for academia. They are quite complex tools, and also the language, the well-known C language, can be easily misused. And the third one is how to prototype and verify, because we cannot do things that we do traditionally. We cannot use LEDs and buttons. Why? Because our designs, by the high-level synthesis, have typically fast clock and complex data. If they don't have, we don't need high-level synthesis in the first place. So this one is not so useful, but instead today we have boards with system on chips. So we have FPGA part, where is our logic, and microprocessor and all the other architecture around that can help us building, let's say, prototyping verification. I have here too. This is Red Pitaya, which is good for signal processing, has fast analog inputs and outputs and all the ecosystem that can be used. And the other is one of the Zinc boards with video interfaces where we can test some image processing circuits. So we prepared laboratory materials. And what we need for preparation of this is usually we don't start with empty, with nothing, just with a task. No, we start with something, let's say a framework. This is, let's say, a framework for a FIR filter. So the instructor needs to prepare this. And not only the model, but also a test bench for the model. Because first we write a model and simulate. And test bench looks like, let's say, C++, we can write a code that reads input data from some files, calls the function, outputs data to the file, so we can visualize it. And this is not all. If we want to go to the board, we have to prepare a project where we will put our box to be able to compile it, do final verification. So what are the exercises we have? First, there are some simulation-only exercises, metrics computation, like doing computation with complex numbers. Okay, this is very simple in C language, but here I have division of probably real values, at least fixed point values, which is not simple case. Then we can take, for example, some small encryption algorithms and implement it. This is just an architecture of algorithms implemented in hardware. And for examples that are good for testing on boards are different filters, which have, let's say, simple structure to implement in their functionality, or for example, numerically controlled oscillators, so generating various waveforms, or some simple graphics, where we just calculate well-known mathematical elements. I first applied high-level synthesis to the third level of study, and used it with some seminars several years ago. And these are some typical student projects from signal processing domain to neural networks to modeling electrotechnical devices. One good one was ray tracing. Okay, these were done by simulation. The projects on the real boards were, for example, video image filters, like this edge detection filter. And we added graphics to our RedPIT system. And we also tried some hardware accelerators on the Zinc board, on the board with processor and FPGA part. So to conclude, is high-level synthesis useful for digital design education? It is, but for the graduate student, because we need a lot of prerequisites. So I introduced this to the second level of the study. There are many tools and also books, and you can get free books on high-level synthesis, but there is lack of good examples the tutor can use for the laboratory part, because everybody has And the last thing, high-level synthesis starts with a promise to be productive, to make a complex design in shorter time to better explore the functionality. This is true, but we cannot expect to be productive during learning. So the learning gap is quite steep. We will not be efficient at this time, but I think it is a good start because high-level synthesis is in digital design of complex integrated circuits, digital circuits used more and more in the industry, and we'll have to follow this also in the education. Okay, thank you very much.
Thank you for your presentation, Andrej. So, we have questions. Ratko? Yes.
Yeah, the high-level synthesis is, it has really it's a really old technology now. It wasn't recently proposed. So, yeah. Can you comment about the maturity level of existing tools for high-level synthesis?
Yes. As I said, these tools are third generation of the tools. So they are, I would say, quite mature. Maybe more than maturity level of the tools is important that we know when to use high-level synthesis. For example, if I design some specific interfaces, I need to go to a lower level where there is specific timing involved, etc. But for hardware acceleration, I think these tools are quite good. And in the design process, we have to combine different techniques. So maybe we definitely not use high-level synthesis for the whole chip. But maybe different parts, even more parts, could be used by more projects in high-level synthesis and then combined together in the final design.
Okay, thank you. Is there any other questions? Okay, if not, Thank you, Andrej.